So let us start. And today we have Pavel Etingof from MIT as a speaker, and he will speak about periodic pencils of flat connections and their p-curvature. Pash, please.
Okay, thank you very much. So let me know if there are any problems with sound or anything. So this is based on two papers that we recently posted right here. And so this is a story about certain differential equations that arise in representation theory and enumerative geometry. And we were able to study their p-curvature, compute the spectrum of the p-curvature. And so that's what I wanted to talk about. So we will consider the following generality. So I will work with a smooth variety over some algebraically closed field K. And most of the time, it's just going to be a affine space or an open subset of an affine space. And I'm going to consider a trivial vector bundle on X with fiber V. You can extend to non-trivial, but this is not going to be a very essential extension. So actually, the case of trivial bundle already contains everything. And so I define a polynomial family of flat connections on X with fiber V as follows. So this is just a family of connections of the form D minus B of S1 Sn, parameterized by, so depending on n parameters, polynomially, and B belongs to, as usual, it's a one form with values in endomorphisms of V. And so they are flat, which means that we have the Maurer-Cartan equation dB minus B commutator B is 0. And I'm going to call such a family a tensor if B depends on the variables S, the parameter S, linearly, homogeneously. So B is equal to S1 B1 plus so on plus Sn Bn. And so in this case, the flatness conditions.
Is that only the dimension of the variety, or that's the dimension of the fiber of V?
N is neither. N is the number of parameters that the condition depends on.
Okay, thanks.
So dimension of variety, I think, will be denoted R. And the dimension of V maybe will denote it N capital. So so the equations for flatness are then looking as follows. So first of all, dBi must be 0, and Bi commutator with Bj is 0. And if X is one-dimensional, of course, these conditions are empty. And now comes the main definition. So the main
the first one, the closedness.
The second one is non-empty because your matrices should commute.
No, there is only one matrix. If n equals 1,
n equals 1.
Dimension x equals, no, sorry.
Not n equal 1, dimension of x equal 1, which is R or something.
No, that's yeah. So what do I want to say? Yeah, so that's right. So no. Sorry, BI are no, they should not. So BI are one forms, and therefore commutator BI with BJ is a two form on a one-dimensional variety. It is 0 even if the matrices don't commute. So it's still the condition is empty. Okay, so now the main definition. So a family nabla of S is said to be periodic if there exist shift operators which implement an isomorphism between connection corresponding to parameter S and parameter S plus EJ, where the J's coordinate has been changed by 1.
Pash, how these shift operators depend on S? Rational, polynomial, meromorphic?
Yeah, it is written here. So this is rational functions. So they lie in GLV
Okay.
over the ring of polynomials on X, so regular functions on X, with coefficients in the field of rational functions of S. So what turns out is that, first of all, such pencils have many remarkable properties, and also there are many interesting examples. So I will first explain some general theory of such pencils, and then I give some examples, and then I will give some more general theory. So I will start with the case of complex field and pick a point on X. And I'm going to, so my variety is always going to be connected. And I can define the monodromy representation, rho S, from the fundamental group of X with respect to X0 to the general linear group. Just monodromy of this flat connection. And let me say that family nabla of S has periodic monodromy if for every J, the monodromy of connection rho S corresponding to monodromy rho S of the connection corresponding to the value S of parameter is isomorphic as a representation of this fundamental group to the monodromy of S plus EJ of connection corresponding to S plus EJ, not necessarily for all S, but for a large set of S, by which I mean a set of S which cannot be included in a countable union of proper analytic subsets of affine space.
Pash, just in case to be pedantic, will you work with analytic topology, or since your K, you know, is an arbitrary algebraically closed field with the risky, can
I will work with both,
Okay.
but at the moment I'm talking about complex varieties, and here when I say that generically rho S is isomorphic to rho S plus EJ, I want it to be true on a set which is big in the sense that it is not contained in a countable union of proper analytic subsets of the space C to the N. C to the N. The first theorem is that if I have a pencil, so these definitions make sense for families, polynomial families, but actually the sharpest results we get are for pencils, and there are many examples which are actually pencils. So a pencil nabla of S has periodic monodromy if and only if its monodromy is defined over some finite Galois extension of rational functions of Q, where Q are exponentials of S, and is Galois stable. So actually, in all examples, it's defined right over C of Q itself, but the proof, I cannot prove it. I can only prove that it's defined over the extension. But really, the statement is that if rho is periodic, that in fact you can write it in terms of trigonometric functions of S, or maybe some algebraic functions of trigonometric functions of S. So let me explain the idea of the proof. So we have a holomorphic map from Cn to representations of pi 1. Well, this is a stack, so you have to be careful, but I'm going to skip that in the talk. But in the paper, it is written more carefully. And this map is Z to the N periodic. Well, it's periodic almost everywhere, so then it's periodic everywhere. And we get a holomorphic map, therefore, from the quotient C star to the n to pi1 to home from pi1 to GLV modulo GLV, to this stack of representations. And now, since nabla is a pencil, differential equation, the right-hand side of the connection linearly depends on S, and therefore monodromy is bounded by an exponential of S. So this means that when I pass to rho bar to functions of the exponential variables, it's going to have polynomial growth. And so this, but that means that if you have a function, holomorphic function here, that has polynomial growth at infinity, then it is actually a trigonometric function. So rho bar is a regular algebraic map. Now, what we want is a map not to the stack, but to the space of matrix representations before quotienting by the basis, because we want to write our representation in a basis in matrices which depend trigonometrically on S. And for this purpose, we need to slice from C star to the n. We need to take a section and go upstairs here. Well, this can only be done in general after an étale cover, and that's why I need this Galois extension. So there is a theorem that in invariant theory that whenever you have this situation, then over étale cover, you can map to here, and you obtain a realization of this representation over trigonometric functions, or rather over algebraic functions of trigonometric functions. So are there any questions? Okay, so this is kind of general theorem. And then another theorem says that if you have a family with regular singularities, then it is periodic if and only if it has periodic monodromy. So periodic in the sense...
What do you mean family with regular singularities? Because there can be ambiguity.
For every S, it has regular singularities.
Okay, this removes first question, and second, your X is non-compact, so which means that
well, irregular singularities actually does not depend on compactification. It means that for any compactification, it has regular singularities on the bound.
Okay. Good, and for each S, so it's
for each S, yes.
All right.
Or you can work over, say, rational functions, polynomials of S, something like that. No, not rational functions. So anyway, for each S, really. Okay, so again, I want to explain the idea of the proof. So of course, one direction is pretty obvious. So periodic means that there are these shift operators. And so, of course, if you have shift operators, then monodromy is going to be periodic. This is pretty clear because you have isomorphism of D modules, isomorphism of differential equations. But the other direction requires proof. And its proof is obtained from Riemann-Hilbert correspondence. So by Riemann-Hilbert correspondence, since monodromy is periodic, this means that for generic S, you actually have these shift operators, but the individual shift operators for each generic S, and we have to show that there is a consistent family which depends rationally on S. And this can be done by using Chevalier's elimination of quantifiers. So basically, if there exists for each S a shift operator for a very large set of S, this means that there exists one which depends rationally on S because this is given by some algebraic equations. So it's there is some technical implementation explained here. If there are questions, I can answer them at the end of talk, but this is technical and not very interesting.
More general question. It looks like you don't use anything more than Riemann-Hilbert. So which means that probably you can include irregular singularities as long as you know the irregular Riemann-Hilbert.
That's correct. Yes, and in fact, you can replace monodromy by monodromy plus Stokes data, and
Mhm.
then you can generalize this. Unfortunately, in that form, this theorem will not be very easy to use because it is hard to, in general, for multivariable equations, to kind of compare Stokes data. It's hard to write down what Stokes data are. I mean, you can, but it's somewhat challenging. But in principle, this is possible. Yes, I agree. And in fact, there are examples where this is used.
Okay.
Other questions? Okay, so all right, so I'm going to skip this formal part a little bit and go to the next thing, which is that there are many examples of periodic pencils, which can be constructed using, which, I mean, we can establish that they are periodic. So the point is it is hard normally to construct these shift operators in many cases. But it is often known that monodromy is periodic and they have regular singularities. So you can use this theorem to establish that they are actually periodic. And later I will explain why it is good to know that they are periodic. So here are examples. So first of all, Knizhnik-Zamolodchikov connections. So these connections are attached to a simple finite dimensional Lie algebra with Cartan subalgebra H. And so if you have weights lambda 1, lambda r in H star, complex weights, and you have an element of Q plus, so root lattice, a positive part of the root lattice, you can consider Fermat modules. So we assume that the Lie algebra, we fix the triangular decomposition, and we consider Fermat modules M lambda with highest weight lambda. So we take the tensor product, M lambda 1, M lambda r, and then we take a particular weight space there. So we take the highest weight and we move down by beta. So this space actually depends only on beta and not on lambda 1 through lambda r, because we can express it as the weight space of weight minus beta in the tensor product of r copies of the enveloping algebra of n minus, the negative nilpotent subalgebra. And then the KZ connection is a connection on the variety X, which is in this case a configuration space, C to the R minus the diagonals. And the connection has the form D minus H bar, which is a parameter. And then there is a summation from I equal 1 to R, summation from J not equal I, omega ij divided by zi minus zj times dzi, where omega is an invariant Casimir tensor. And so it is well known that this connection is flat and it is a pencil. So if you write down, there is one parameter of the pencil that is apparent here, but there are other parameters which are lambda, but it's actually a pencil with parameters h and also h lambda 1, h lambda n. So if you compute in matrices what you get here by trivializing this tensor product, as I said, using enveloping algebra, you discover that the matrices on the right side are linear in these variables, h, h lambda 1, and so on up to h lambda n. So there are, so these are actually not variables, but these are weights. So the number of parameters here is 1 plus for h plus r, which is the dimension, times the rank of the Lie algebra. And the proposition is that this is a periodic pencil. Well, maybe up to rescaling this S by some small integer.
Pasha, can you please comment in this particular example what is periodic, just as practical as possible?
Okay.
Because
So-
our matrix depends
this means-
on Q
okay.
in the power, so that's it.
So there are. This means that there exist shift operators which move these, which change these variables by 1. And
By one, what? We are doing lattices, right? Some by one. What is by one?
so you can add to them.
Some basic vector.
Yeah, so like H,
Yeah, you can add.
Only H is, changes to H plus 1. But what about lambda 1, lambda 2,
To each
lambda?
coordinate one. To
Each,
each
so
coordinate
there
of
will
this
be
vector,
many
you-
shifts, right, by is, right? We're doing weights. My problem is about because of weights, the appearance of the weights here.
yeah. You can move lambdas also. Yes, so yeah, you can also move lambda I by an integer multiple of 1 over H.
But if you assume that G is SL2, so then
Yeah, then there will be okay, then they're just scalars. Anyway, and so well, the shift operators which change lambda by which shift lambda are actually well, something that one can compute. It is the so-called
By row, sometimes it's by row, you know, right? Somewhat complicated, right? Shifts by row somehow appears.
No. We can shift by every fundamental weight.
By every fundamental weight, yeah.
Yeah.
Good. Let's go.
But the most difficult operator is one shifting with respect to this first variable. So the other ones are not so difficult. And so this says that this is periodic, and the proof is the following, that first of all, it is easy to see that this has regular singularities. And so it is enough to show that monodromy is periodic, and this follows from the Drinfeld-Konner theorem. So what does Drinfeld-Konner theorem say? It says that monodromy up to conjugation is expressed through R matrices of the quantum group UQ of G. And the quantum group, it depends on Q, which is e to the pi I h, and also Q to the lambda I, which is exponential of pi I h lambda J. And so that exactly means that it's exponentials of those S, and monodromy is periodic. And one can generalize it to Knizhnik-Zamolodchikov equations for Kac-Moody algebras, which works the same way. Also, one can consider Lie superalgebras. In this case, the monodromy theorem was proved by Nathan Gear, and so we can use that. Also for trigonometric KZ equation, which actually reduces to the rational one, for elliptic KZ equation, for which it is also known that monodromy is given by R matrices, for Knizhnik-Zamolodchikov for the Deligne category, and so on. So there are many.
Do I remember correctly that there exists irregular degeneration of trigonometric?
Exactly, yes. There exists an irregular degeneration of trigonometric KZ, which is the equation considered by Felder, Markov, Tarasov, and Varchenko, and it commutes with the Casimir connection. So for that equation, so those pencils with irregular singularities, actually it is known that periodic pencil, we will see the theorem, is always has regular singularities. When pencils are irregular, what will happen is in some parameters they will be periodic, and in other parameters they will be infinitesimally periodic, which means that instead of shifting by one, they are periodic. There is just a connection, a continuous connection in the direction of that parameter, which commutes with our equation. So this means that they are periodic with any period. Actually, they are just constant in that direction. And but that theory can also be developed, and this is in our paper too. Jan, you have? Does it answer your question?
Yes, it does. Good, thank you.
All right, so here is a second example, which is Casimir connections. So this connection was introduced by De Concini and independently Toledano Lareda, and also Felder, Markov, Tarasov, Varchenko. And this is a connection on the regular part of Cartan subalgebra of our Lie algebra, which has fiber which is weight space, but just in one Fermat module, m lambda, of weight lambda minus beta. And it's given by the formula d minus h bar. And here is going to be a sum over positive roots of Casimirs for the SL2 of this root without the Cartan part, but you can also include it, it doesn't matter, multiplied by this logarithmic form, d alpha over alpha, where these are root elements of G. And this is known to be flat, and it forms a pencil, and parameters of this pencil are again H and also H lambda. And so the proposition is that this is a periodic pencil up to, again, rescaling S by small integer. The proof is the same. So we have regular singularities. And then we use the theorem of Andrea Appel and Valerio Toledano Larreda, who computed the monodromy of this connection and showed it is given by quantum Weyl group for UQ of G. And quantum Weyl group appeared in the work of Lewandowski and Soibelman. Also, it is the quantum braid group action by Lustig. So this quantum Weyl group again depends on Q, which is e to the pi I h, and Q to the lambda. So we get periodicity. And there are generalizations. Again, you can consider Casimir connections for Katz-Moody algebras. This is also done by Appel and Toledano Larreda. Also, one can consider trigonometric Casimir connections, which act on vector bundle with fiber being representations of the Yangian. And so in that case, also there are monodromy theorems. So one can prove that these are periodic. Another example is
in this case, the X is still the affine space with R being the rank of the Lie algebra.
Yeah. So in this case, this is in the Casimir connection. The connection is on the torus. So not on the Lie algebra, but on the actual maximal torus of the corresponding group.
Also
the same dimension, yes, but it's a torus now for the
thanks.
trigonometric connection. And then there is Dunkl connections. So these are the following. So we have a finite Weyl group. There is a reflection representation H. And in this case, V is a representation of this Weyl group. And the Dunkl connection is the connection on the regular part of H with fiber V. And it looks like D minus H bar times the sum over the reflections of W of reflection S multiplied by the logarithmic form d alpha S of alpha S. This is known to be flat, and this is a flat pencil with parameter H bar. So here we have only one parameter. And this is an example where shift operators are actually known explicitly. They can be written in terms of Obdam shift operators. And so one can...
The summation is on the, not all order 2 elements of Weyl group.
No, only reflections, let
me correct it. Shift operator is only in symmetric theory. Dunkl operators are used indeed. But
yeah, but it's the connection...
Symmetric or anti-symmetric polynomials.
Yeah, that's true. But this connection has rank order of the Weyl group. And as a D module, it is equivalent to the Calagera-Moser system. And for that system, there is a shift operator.
But it is not Obdam, whatever, Obdam's one. Something different, I believe. Different, for sure, right? The formula, this famous formula, symmetrizer, antisymmetrizer by another antisymmetrizer is literally, it can be applied only to symmetric, right? Or anti-symmetric equivalently.
No, but there is a differential operator. No, there is a...
You're absolutely right. It will depend on Q, which is e to pi IH. And of course, it is periodic because of your definitions, right? This is true.
No, Vanya, so shift operator is a differential operator which intertwines Calagera operators with parameter C with Calogero operators with parameter c plus 1.
Right, but Obdom's operator is very specific. Anti-symmetrizer with respect to y divided by anti-symmetrizer with respect to x, you know, right?
That's right. And so this operator will provide this. You can rewrite it to make it shift operator for this problem.
Yeah, but you cannot apply it to non-symmetric polynomials. It will not work. Only to symmetric. You need to do. You can do something. Okay, let's go
Yes.
on. Right? We will discuss later.
Right. And so this is a periodic pencil, but in any case, well, there is a proof that is not based on this construction of shift operator, because again, it has regular singularities, and we know that monodromy of Dunkl connection is given by the Hecke algebra, HQ, where Q is e to the 2 pi I h. So this is a result of Ginzburg, Gway, Obdom, and Rouquier, the so-called KZ functor. And so this gives the proof. And one can generalize this. One can consider Dunkl connections for complex reflection groups or trigonometric Dunkl-Cherednik connections. And so these are also going to be periodic. And here is an example that comes from enumerative geometry. Suppose you have a conical symplectic resolution of singularities with finitely many torus fixed points. Actually, it's bad that I'm calling it X. Maybe, well, this is not the same X as before. And so, so in this case, I can consider the quantum connection nabla X, whose base, which is the old X, is the second cohomology of this resolution without the divisor of poles and fiber H star of X tilde. So I'm talking about examples when it is actually known that it is conjectured that it's always quantum connection always has rational coefficients, and on the so maybe I should mod out by the cohomology. This is cohomology with coefficients in C star, which is a torus. And so this is a flat family which depends on equivariant parameters S1 through Sn of some torus acting on this X, and it is known to be a pencil. So it's in a certain basis, which is called stable basis. It is actually linear in the equivariant parameters. And then one can show that it's a periodic pencil. And this can be extracted from, so in this case, the shift operators have been constructed geometrically. They can be constructed using stable envelopes.
Can you recall how the shift operator, because I don't remember. I believe that the basis which you use is correspond to stable envelopes, but why it why it's
well, there is this is a complicated story which I don't know very well. So, but they do construct shift operators geometrically. This doesn't mean that they can compute them explicitly, but they can be defined, which is enough for our periodic property.
Okay.
Well, this is a very complicated story, though. Okay, but now I start to explain why it is interesting to consider periodic pencils. And so one interesting property of these pencils is that they have very restricted conditions on singularities. So one important property is that their singularities can only occur on hyperplanes in the space of S parameters. And moreover, on hyperplanes, which are defined over Q, at least up to shift by a constant vector. So this echoes the fact that we know well from representation theory, that in representation theory, we get singularities where some interesting things happen with representations. But for some reason, they always occur on some, well, almost always, like, well, except Virasoro algebra maybe, but for some things related to simple Lie algebras or Weyl groups or things like that, they always occur on hyperplanes. And moreover, hyperplanes with rational coefficients. And so to some extent, this theory explains it because these periodic pencils are strongly connected to representation theory.
But do you mean these regular singularities which you promised somewhere that for some rational hyperplanes in SIs, your periodic pencil will have regular singularities in some other variable, so what?
No, it always has regular singularities, but by singularities, I mean that this shift operator is going to have poles. It is impossible
okay.
that it will be completely regular. And so it has poles. Other things are like monodromy can become non-semi-simple, for example. All kinds of phenomena like that happens on hyperplanes.
Okay, good.
So here is an example. So let us denote by Bj the set of points where nabla of S is not isomorphic to nabla of S plus Ej as a connection. So as a D-module. And let's take Bj bar to be the risky closure of this Bj. Well, then Bj bar is contained in the pole divisor of this shift operator Aj. Now here is a theorem that at least if I look at codimension 1 irreducible components of this variety Bj bar, then this is just a hyperplane. Every codimension 1 irreducible component of Bj bar is just a hyperplane defined over Q up to shift. Moreover, if nabla of S is generically reducible, then poles of Aj bar, when you project it to PGLV, because of course you can multiply by any scalar function and tells you nothing, but the canonical thing is projection to PGLV, and this projection can have poles only on hyperplanes like this. And similar results occur for other types of singularities, nabla of S, such as non-semi-simplicity loci, for example, where it is not semi-simple, or jumping loci of endomorphism algebras, where the endomorphism algebra becomes bigger, or something like that. So all of them obey this very restrictive rule that singularities must occur in hyperplanes. And let me explain why this happens. So for the proof, we use the following theorem, which is interesting in its own right. And in fact, it's interesting because it is proved using characteristic P. So this proof will come later. But the theorem says that every periodic pencil has regular singularities. So in fact, so this was about question of irregular singularities. So for irregular singularities, this theory works a bit differently. So some periodicity along some parameters is continuous rather than discrete. So this is proved using p-curvature, which I will explain below. But let us assume the theorems 8 now and prove the previous theorem about singularities, that they can occur on hyperplanes. Well, that actually is obtained from a theorem of X. It's a simple corollary, actually, of theorem of X. But in general, this kind of theorems went into what is now model theoretic methods in algebraic geometry. So let Y in Cn be an irreducible algebraic hypersurface. And assume that it has the following property, that its exponential is in the torus C star to the n, is also contained in an algebraic hypersurface. Then Y is actually a hyperplane defined over Q up to shift. So this is a very nice and rather easy theorem, so it's actually can be proved on one page. But the proof of our singularity theorem is the following: that by theorem 8, we know that our pencil has regular singularities. So by the Riemann-Hilbert correspondence, so we want to study the set of S where nabla of S plus J is not isomorphic to nabla of S. But Riemann-Hilbert tells us that this is the same as the monodromy rho S plus J, S plus EJ, is isomorphic to rho S. So we need to study the set of points where rho of S plus EJ is not isomorphic to rho S. But we know that rho S, by the first theorem that we explained, is defined over trigonometric functions, over some finite extension over the field of trigonometric function. And this means that the bad set for rho S is, which is exponential of this Bj bar, is an algebraic hypersurface, is contained in an algebraic hypersurface in the torus. So we have an algebraic hypersurface, which is a component, codimension 1, of this Bj bar, whose exponential is contained also in algebraic hypersurface. And so by Ochs' theorem, it has to be a hyperplane defined over Q up to shift. So any questions about it?
No, it's pretty much clear. Because of the previous theorem, of course.
Yes.
This previous theorem had kind of a toy model that the endomorphisms of the algebraic torus, it's basically just monomial maps. It's kind of a very, very toy model of this X theorem.
Yeah, well, but this X theorem, it's actually a functional analog of theorem of Gelfand and Schneider, which says that if you have a number such that it is algebraic and its exponential of 2 pi I times this number is also algebraic, then this number is a rational number, and the e to the 2 pi I of the number is the root of unity.
Exactly.
So actually, I will mention this theorem below. It will be used. But this is a functional version of this theorem, which is, of course, much easier because it deals with functions as opposed with numbers.
Pasha, you actually need really little something to have the same theorem that all monodromies of your parameters, like k, etc., they are exps. They go through exp 2 pi I or whatever, pi I k, right? Monodromy is in terms of exp of.
That's right. Like that's what I say.
There can be many situations which are beyond what you discuss, I believe, right?
The theorem 1. This is the theorem that if you have a periodic monodromy, so the theorem says that if you have a periodic pencil, then its singularities occur on hyperplanes, and we know that periodic pencil by theorem 1, its monodromy is defined over trigonometric functions. So
right, because we have reduction to rank 1, and then explicit calculation, sometimes very explicit, right?
No, this is a very please
recall to Vanya theorem 1.
Sorry, go ahead, please. Yeah, good.
Please recall theorem 1 that something is defined of algebraic extension, then will be clear, because probably Vanya missed the beginning.
Yeah, the theorem says that monodromy of a periodic pencil is defined over trigonometric functions, or more precisely over algebraic extension of trigonometric.
Okay, good.
Now I'm going to finally consider the main topic of this talk, which is the same story in characteristic P. So let me first recall that in characteristic 0, if a connection is flat, which means it has zero curvature, then it has a full set of formal flat sections near every point. In analytic theory, it has a full set of formal analytic sections on some disk around this point. However, this is false in characteristic P. For example, if you consider the equation dy over dt equal to y, then it has no non-zero formal solutions near 0. because the solution in power series of this thing is exponential of t, which is sum of t to the n over n factorial. And this is only defined in characteristic 0 because these factorials contain all primes. And that's because connections in characteristic P actually, besides usual curvature, have another kind of curvature which already exists in the one-dimensional case and which was defined by Grothendieck and called the p-curvature. So it's very easy to define. So p-curvature is the following. So we have these covariant derivative operators, nabla I, with respect to some coordinates. And then p-curvature is the collection of operators which have just piece powers of these covariant derivatives. And so it is known, the differential part of this operator goes away. This is just pure matrices. So they belong to K of X tensor with endomorphisms of V. So there are no derivatives. And this is because if you raise derivative to piece power, it becomes the zero operator on functions. So for example, for the above equation, the connection operator is d minus 1 for the exponential function. So the curvature, p-curvature is nabla to the p, which is d minus 1 to the p, which in characteristic p is d to the p minus 1, and d to the p is 0, so it is just minus 1. Now, why does this thing has to vanish in order to have a full set of solutions? Well, if you have a flat section F, which means nabla I to the F, nabla IF equals to 0, then of course nabla I to the P times F is also 0, and therefore Ci of F is 0. So that means in order to have a fundamental set of formal solutions, we need to have all Ci to be 0. For example, if Ci is invertible for some I, this means that we have no non-zero solutions at all. If Ci is not invertible but not 0, this means that we will have a dimension of the space of solutions will be smaller. So for generic X, the dimension of the space of formal solutions, which will be actually a module over this ring of quasi-constants, which are formal series in xi to the p, is the dimension of the common kernel of this operator Ci of X at the point X in X. And so this is a free module, and it has a basis of algebraic functions. So, so here is the next theorem, which is actually the main theorem of the talk. And this theorem says the following. Suppose nabla of S is a periodic pencil parameterized by S1 through Sn. Then the p-curvature operator Ci of this pencil, well, we cannot compute them, but we can compute their spectrum, namely their isospectral of to the operators, which are the following: sum from j equal 1 to n, Sj minus Sj to the p times Bij 1. So this Bij are the, so I have these differential forms. One forms Bj, which is the sum of Bij times dxi. So Bij actually matrix functions. And 1 means that they are Frobenius twisted, which means I raise every entry of the matrix to piece power.
Pash, isospectral means what?
Isospectral means that they have the same, it means that if you have these are commuting matrices, basically. Well, they are matrix functions, so they are commuting matrices over the field of functions on X. And so isospectral means that, well, this defines a module over the polynomial ring, finite dimensional module. And this means that these modules have the same composition series. So more precisely, okay, so you could also say that if you take any linear combination of these Ci's and the same linear combinations of these things, those will have the same characteristic polynomials. Does it answer your question?
Yes, to some extent. But yes.
Yeah. Like if you had a one-dimensional connection, this would we would just have one operator C and one operator here, and being isospectral would mean that they have the same characteristic polynomial.
Okay.
So this is a striking fact, because in general, if I write a kind of random differential equation, and even some nice differential equations such as Lamé equation, or more generally Hitchin equations, you cannot compute these eigenvalues in any explicit form. So, for example,
we need eigenvalues. You need characteristic polynomial for this definition. Why you need exactly eigenvalues? This can be difficult.
Oh, well, yeah, characteristic polynomial or eigenvalues is basically you can go from one to the other.
Okay.
So it basically says that when you compute spectrum of the p-curvature of an equation like this, what you need to do is you need to take a semi-classical limit. So you need to kill the derivative and Frobenius twist the right-hand side and replace all parameters by their Artin-Schreier images. So that's what it says in a very general setting of these periodic pencils. And let me explain the proof, because it's very instructive and simple. And I will restrict to the one-dimensional case just to simplify the exposition, because it changes nothing at the level of ideas. So in this case, I have a connection, and let's also assume that I have just one parameter. So n equals 1. So also doesn't change anything. The idea is the same. So my connection is just an operator on the one-dimensional manifold d minus sb. And so C of S is the p-curvature of this nabla. So it's a function of coordinate x on this x. So now I have this periodicity condition, nabla of s plus 1 is isomorphic to nabla of s, at least for generic s, so by some rational function. And so this means that the p-curvature, cs plus 1, which is just the p's power of this thing, has to be conjugate by the same map to C of S. And this means that if I take the coefficients of characteristic polynomial of C of S, which are traces of exterior powers, and call them bi of S, then they are periodic with period 1.
Pasha, but before this, it was a complex theory. Right now, you're switching to a characteristic P. Why shift operator exists exactly in the same style? Why it is granted?
By definition, I'm considering periodic pencil. What we'll do later.
By definition, of course. No, not because of some reduction from complex to.
No. Later we will do reduction and show that for large P, we have if we have a periodic pencil and characteristic 0, we can do a reduction mod P for large enough P and obtain a periodic pencil and characteristic P. So, so that's a kind of interplay between complex analysis and characteristic P. We will use complex analysis to show that some pencils are periodic by using monodromy. And then we will reduce these connections to characteristic P for large enough P and use the fact that they're periodic to extract information about their behavior and characteristic P. Okay, so we have BI is periodic. And also, we know that this nabla of S is linear in S. So this means that nabla of S to the P, which is the p-curvature, is a polynomial of S of degree P. And this means that the coefficients of characteristic polynomial are polynomials of S of degree P times I, where I is the number of the coefficient. So the trace of wedge to the I. But now, this equation means if you have a polynomial in characteristic P, which is periodic with period 1, this means it's a polynomial of the Artin-Schreier function, S minus S to the P. So BI of S, therefore, is some other polynomial, beta I, of S minus S to the P. And this beta I is already a polynomial of lower degree. It's a polynomial of degree I. Another thing I know is that when S equals 0, my connection is trivial, so its p-curvature is 0. And this means that the matrix C of S is divisible by S. All elements of this matrix are divisible by S, And this means that the minors bi of S, it's a sum of minors of size I, is divisible by S to the I. So we have a polynomial of degree I applied to S minus S to the P, and this is divisible by S to the I. That can only happen if this polynomial is a single monomial, which is U to the I times some constant, beta I0. So this, we pinpointed this polynomial up to a constant. It is just U to the I. And it remains to calculate this beta I0. And for this purpose, we can send S to infinity in the sense of algebraic geometry. So look at the leading term. So the leading term of the p-curvature is minus S to the P times B to the P. So this implies that this beta I0 is the ith coefficient of characteristic polynomial of B to the P. But this is the same as ith coefficient of characteristic polynomial of B1, because B1 and B to the P are actually conjugate, because eigenvalues of B1 and B to the P are both piece powers of eigenvalues of B. And this implies that C is isospectrum to, well, so we have this Artin-Schreier thing times B1. So it's isospectral to S minus S to the P times B1. And that completes this proof. So this is, and the proof in general is completely parallel to this.
Pasha, did you use that B are some from matrices and all it's their entries are powers, P powers, right? You remember the definition. It seems that you did
B1, no, we got matrix B to the P. So there are two matrices. One is B to the P, which is the usual piece power of the matrix.
You consider because of p-curvature, you consider some piece power of the entries of the matrix, right?
No. There are two matrices here. One is B to the P, which is usual piece power of the matrix B.
From the definition of p-curvature, right? Oh,
Yes,
okay.
from the definition of p-curvature. The other matrix is B1. It's a much simpler matrix,
Okay.
where we take just every entry of B and raise it to power P. These are different matrices, but
yes,
they are isospectral. They have the same eigenvalues, and therefore the same characteristic polynomials. And the same eigenvalues, because eigenvalues of B to the P are piece powers of eigenvalues of B. And eigenvalues of B1 are also piece powers of eigenvalues of B, because entries of B1 are piece powers of eigenvalues of entries of B. And raising to piece power is a field automorphism. So if we raise all entries to power P, this will also raise eigenvalues to power P. Okay, and so any questions?
So
All right.
Sorry to interrupt. So I get the feeling that you are working on in the restricted enveloping algebra, or
I don't work in any enveloping algebra.
There is no Lie algebra.
There is no Lie algebras. It is just matrices.
Well, I mean, so for
Yeah,
so
that's right. So in
P,
some sense, yes, I am working in the
you are
restricted.
the abelian Lie algebra you are working in.
Not abelian, no, matrices, Lie algebra, GLN. It's a
That's
restricted
right.
Lie algebra.
That's right. Because the P, we take the
Yes.
Frobenius quiz.
Yes.
That's the P1 is.
Yes. So then I do work in Lie algebra, GL of V. Yes, that's right. Okay, and so here is a corollary that the p-curvature of a periodic pencil is nilpotent when parameters lie in FP. Well, what happens when parameters lie in FP? So in the theorem, we say that it's isospectral to this thing, but if Sj are in FP, then this prefactor is 0. So this means that Ci are isospectral to 0. That doesn't mean that they are equal to 0, but it means that they're isospectral to 0, which means that being nilpotent. So that's a very important corollary. This theorem gives information about p-curvature of connections in the examples I considered. because they can be reduced to characteristic P for almost all P. So, so that's what Vanya asked. We take these connections in characteristic 0 that we know are periodic, even though we cannot always write down effectively all the shift operators, and we reduce them to characteristic P, and there we can use this theorem to say something about their p-curvature. Now, I want to remind that this connects well to the work of Nick Katz, who made the following definition in 1970, which was very influential. He said that a flat connection defined over Q bar is globally nilpotent if its reduction to characteristic P has nilpotent P curvature for almost all P. And the theorem that we obtain, therefore, that a periodic pencil defined over Q bar evaluated at rational values of Sj is globally nilpotent. So in particular, all our examples with rational values of Sj are globally nilpotent. So this gives, in general, it is very hard to check that some connections are globally nilpotent because you have to check infinitely many primes. But here we obtain a whole lot of examples of non-trivial connections about which we know that they are globally nilpotent.
Pasha, may I make here a remark, actually a question, right? But you are approaching the end. So if you have explicit formula for the shift operator, then you can easily move it to any characteristic P, sufficiently large characteristic P, right?
Exactly, yes.
For instance, Obdom's operator, perfectly defined for almost all P's, right?
Yes.
And then it is immediate, right? But you're doing some stuff which is beyond explicit formulas for shift operators. You need
because I don't know how to write them. For example, for KZ equation, it is not.
But do you have a single example when we don't know how to write shift very explicitly? We know that they exist, and then the point is just to find some combination, proper combination of whatever pseudo-differential operators or maybe something.
No, it is hard. Well, I mean, geometry. The ultimate answer is enumerative geometry. It gives you, in many of these examples, a way to construct these shift operators, but it also doesn't cover all the cases. And so I don't know, for example, and in any case, it won't be an explicit formula. It will be a geometric formula, which will involve some complicated functors.
What about examples from 1 to 4? Do we have explicit formulas in these examples?
I think in very few examples.
Very few. Mm-hmm.
Okay, so here is a theorem which explains why periodic pencil is globally nilpotent. And important theorem of Nicholas Katz in 1970, why this notion is useful, is that any globally nilpotent connection has regular singularities. So he also showed that any geometric connection which comes from Hodge theory is globally nilpotent, and also that any global nilpotent connection has regular singularities. And this gives a proof of the theorem that we used before, that periodic pencils have regular singularities. So because periodic pencils are globally nilpotent at rational points, they have to be defined over Q bar, but there is a kind of abstract nonsense technique how to, if it has some transcendental parameters, you can kind of project them to Q bar by making them variables. So that's a standard trick, which I won't explain, but it's not a problem. And so what we obtain is that every globally nilpotent connection has regular singularity. Every periodic pencil has regular singularities. So now I want to talk about geometric connections. So there is a theorem of Katz that says that if a connection nabla is geometric, which means semi-simple and irreducible constituents are direct summands of Gauss-Manin connections for some families of projective varieties, then this connection is globally nilpotent. And the converse for semi-simple connections is a conjecture. It's a conjecture which is called the wide open conjecture, which is called the André-Bombieri-Dwork conjecture. So the André-Bombieri-Dwork conjecture says that if you have a globally nilpotent connection, then it has to come from a family. Then if it's irreducible, it should come from a family of algebraic varieties. And this is, of course, we have no idea how this could be proved, even though for some classes of connections, such as rigid local systems, which have no deformations, Katz was able to prove this using method of middle convolution. And this generalizes Grothendieck-Katz conjecture, which is also wide open, that says that nabla, if nabla has zero p-curvature, not just nilpotent, upon reduction to almost all primes, then it has finite monodromy, which means algebraic fundamental solution.
But what about conjecture that the solutions are rational, right? You know, some standard Grothendieck's
Grothendieck-Katz conjecture, yes. This is also wide open. And this André Bambieri-Dwor conjecture is a generalization of them. If you weaken the assumption,
upon some nilpotence condition, all solutions are just rational, right? If locally
no.
are rational, then
Zero.
they're rational,
Zero
right?
p-curvature means rational solutions, or
Okay.
algebraic rather. Nilpotent p-curvature means solutions can be represented as integrals. They have integral.
So just to refresh how it works. So thank you. Yes.
Yeah. Okay, so we don't know if all periodic pencils are geometric. We know that many of them are geometric. So being geometric means that there are integral formulas for solutions of differential equations. And for for many connections, we know this. Like for KZ, there are formulas of Shechtman and Varchenko. Then for Casimir connection, there are some formulas from Felder, Markov, Tarasov, Varchenko. But in some examples, it is not known despite many efforts. For example, for Dunkl connections, for exceptional groups such as E6, it is not known how to write integral formulas. For some special values of parameters with a lot of difficulty, some people like Heckman and Luyenko, for example, were able to find formulas, but they are very special to those values of parameters. So this gives us a lot of explicit examples it's not just this conjecture is open, but there are some very explicit differential equations which are known to be globally nilpotent and not known to be geometric. And I don't know if I should just not believe the conjecture or should believe and try to prove it for those examples. Okay, so, and finally, the last part of the talk, I want to talk about quasi-geometric connections. So quasi-geometric connection is a kind of more general notion and which is easier to define. It doesn't refer to any geometry, but it postulates a property that geometric connections do have. And so definition is that a regular flat connection is defined over Q bar is quasi-geometric if its monodromy representation is also defined over Q bar. So it is defined over Q bar both in the de Rham and in the Betti realization. So we have Riemann-Hilbert map between Betti and de Rham, which is an equivalence of categories, but it's a transcendental map. It doesn't map algebraic things to algebraic things in general. But we ask that the connection is defined over Q bar in both settings. So this is kind of similar to Gell-von-Schneider theorem, but it's a non-abelian Gell-von-Schneider. So pencils in examples 1 through 4 evaluated at rational points are quasi-geometric. So we know that because we know their monodromy. Because monodromy is expressed as in terms of Q, which is a root of unity, and so it's quasi-geometric. And also every geometric connection is quasi-geometric, since monodromy can be implemented. If you have a geometric connection, which comes from Gauss-Manin, then you have integral formulas, and when you go around a loop on the base, what happens is the cycles in the fiber on which you integrate restructure, but that happens in cohomology over Q, and so that means that we have monodromy representation is defined over Q, but if you take a direct summand, it's defined over Q bar. And so here is a theorem which generalizes monodromy theorem in Hodge theory. So in Hodge theory, we have this basic theorem that Gauss-Manin connection monodromy is quasi-unipotent around divisors on the base. This theorem says that, in fact, this property holds for quasi-geometric connections. So every quasi-geometric connection has quasi-unipotent monodromy along divisors in a compactification of the base. And the proof is actually very simple. It repeats Brice-Korn's proof of the monodromy theorem, which you can find in Delign's book on regular differential equations from 1970. And it says the following, that suppose you have lambda, which is an eigenvalue of the residue of nabla on a codimension 1 component of the boundary, then e to the 2 pi I lambda is an eigenvalue of the monodromy of nabla around this component. Now, if nabla is quasi-geometric, this means that both have to be algebraic numbers. And then we can use the theorem of Gelfond and Schneider to make sure that this number is in Q, which means that this eigenvalue is the root of unity, which is exactly what it means to be quasi-unipotent. So this is a 55-year-old proof of this monodromy theorem by Brice-Korn, which can be used in this more general setting. And finally, I want to finish with an aside into the theory of tensor categories, which is my favorite subject. So suppose you have C, which is a braided fusion category over the complex numbers, which means semi-simple braided tensor category with finitely many simple objects. Then we can consider braid group representations for this category. And braid groups are fundamental group of configuration spaces. So by the Riemann-Hilbert correspondence, those define some differential equations on those configuration spaces, which we cannot write, but which exist and are unique. And more generally, in higher genus, are going to be mapping class group representations. So those will be local systems on configuration spaces of curves. And local system on moduli spaces of curves. And so the conjecture is that all of these differential equations are quasi-geometric. And here is some evidence for this. So suppose my category is representation category of a vertex operator algebra, which is a strongly rational vertex operator algebra. So this basically, this is a bunch of conditions which can be found in the paper of McRae, but which guarantee that you have a representation category which is a braided fusion category. And suppose this algebra is defined over algebraic numbers, which I hope is always the case, because I hope that such algebras are rigid. They don't have deformations, because they're in some ways similar to things like simple Lie algebras. And many examples are known to physicists, but all of these examples are discrete. They occur discretely. They don't have continuous parameters. And when something doesn't have continuous parameters and depends on finitely many parameters, then by abstract nonsense, it is defined over algebraic numbers. And then I claim that in this case, this conjecture is actually true. So these differential equations, which we cannot write, nevertheless have a remarkable properties that this is quasi-geometric. And the proof is very simple. So, but it uses some deep theorem. So the corresponding connection then is the KZ connection for this vertex operator algebra. So we can actually write it, and it is defined over Q bar. And the monodromy of this connection is also defined over Q bar by something that is called Ocneanu rigidity. So Ocneanu rigidity is a statement that braided fusion categories have zero cohomology and do not have non-trivial deformations. And because of they are
Plural
defined,
deformations push over what?
or just, well, they're objects defined over, let's say, complex numbers. So this is just a bunch of matrices satisfying some equations, the algebraic variety. And what it says that this algebraic variety has finitely many points. They don't have deformations. But if you have an algebraic variety defined over Q bar, which has finitely many points, then every point is defined over Q bar. So this implies that all braided fusion categories are defined over Q bar. This is a theorem of Okeanou, which was generalized by myself, Nikšić, and Ostrich to the most general braided tensor categories, actually all tensor categories, fusion categories. And so this proves that this connection is, these representations are over Q bar in both the Ram and Betti world. So this certainly doesn't give a general proof, and there are some very concrete braided fusion categories, such as Greenfield center of the Hagerup subfactor fusion category, which does not, for which we don't know this fact. But in general, this fact could be an explanation of why in conformal field theory, we very often find integral formulas for conformal blocks. Well, because the connections are quasi-geometric, and it is hard for them to be quasi-geometric without being geometric. In fact, it is possible that all quasi-geometric connections are geometric, and this would explain why we see integral formulas so often. Okay, thank you very much.
Thank you.
Thank you very much, Pasha.
Thank you.
As for the last thing, you really, if you want to approach in the similar way the general conjecture, you need to have some information about this sort of R matrices braiding in your category, yeah, for a pair of simples.
No, no, there are very simple examples like this Hagerup category. I know what the R, it is known what the R matrices are.
So then what's the you cannot compute the Hochschild homology of the category?
No, it is zero, and it is defined over Q bar. So everything is fine, but the problem is in the de Rham realization. Actually, I expect,
Okay,
maybe I should
right,
mention,
right. Yeah.
maybe I should mention that you are correct, that I do have an idea how we can prove this here, this conjecture, without using vertex algebras, because there is, of course, a big open question is which braided fusion categories come from vertex algebras. And in the case of Hagerup, we don't know a vertex algebra that defines this category. But I propose a method of proof which will not use any of that. And the method is the following, that in the de Rham realization, we can also talk about braided tensor category using so-called Teichmüller towers, which are described in Delign's letter to Greenfield and explained in detail in the book of Bakalov and Kirillov in 6th and 7th chapter. This is a collection of local systems on configuration spaces which form a factorization category. And if we can prove that our category is finite, is kind of described by finitely many parameters in that language, which means that we can actually determine it by local system, finitely many de Rham local systems on some finitely many spaces. And we can run the argument with rigidity. So it should be rigid because it is the same notion. And so it's also finitely many parameters. The abstract nonsense should imply that in the Ram world, it is also defined over Q bar. So in some sense, I want to say that it is obvious, like you were suggesting, but I don't know how to say it so that it would be rigorous. So
Pasha, let me make it even more obvious. If it is rigid, right? Then if monodromy is not algebraic, then it is transcendental one, at least, right? There will be continuous parameter. At least you can go to p-curvature, you will get continuous parameter. Continuous parameter means it's not rigid, almost representation of the corresponding monodromy group, you know, right?
yes.
It is a sort of formal, you know, right? Not too deep. Maybe it is exactly what Okeanou did, actually, you know, right?
Yes. It is exactly what Agneanu did, and we extended to general case.
Property which guarantees that everything will be over algebraic numbers. Otherwise, it will be continuous parameters, differential.
Exactly. Yes, but I need to do the same in the de Rham realization. In the de Rham realization, I need to show
super strong. If you know rigidity, it is super strong, of course, right?
Exactly, yes. But I need to do the same in de Rham realization. So I need to show that it is kind of that moduli space of such structures is an finite algebraic stack of finite type.
Yeah,
So
you need
that's what I
something.
need.
Yeah, I
But
agree.
that's what you said, that Deligne suggested to interpret the whole structure as a collection of compatible sort of.
That's right, but it doesn't look like finite at first sight. So you have to show that everything is determined by finite amount of data.
Yeah, that's the main point. Pasha, I also wanted to ask you about this finite characteristic story. There is an either a trigonometric analog at roots of unity.
Yes, that's a very good question. There is a trigonometric analog, but it's more complicated. So first of all, there is a notion of p-curvature, which is very easy. If you have a difference connection which shifts by some step, like multiplicative step, q, then if q is a root of unity, you can apply it n times to come back to the same point, and you have this kind of matrix product, which plays the role of p-curvature. And it should be, the same theory should work. The only problem is the technical one, that we used heavily here the fact that our connections were pencils, which means they depended linearly on the parameters. The proof that I gave used that fact. So in the Q difference world, in characteristic 0, or even in the difference world, but in characteristic P, but with difference operators, where we shift by 1, we are not going to have most of the time this linear condition. And we need to somehow understand what happens. So I cannot handle all of these examples in that way yet. But I am pretty sure that the statement should be true and everything should extend.
May I say a little something?
And we are, this is a subject of our current work with Sasha Varchenko. And there were some computations done by Andrei Smirnov, which suggests that this will work. And I also have proof in some special cases. So we are slowly building this up, but we're not there yet.
Yeah, to your question, you see, the story is somewhat opposite. You do it p-adically first, and then it is pretty much predictable. You have p-adic hypergeometric function, everything, and then instead of what Pasha described to us, right, p-curvatures, etc., you will have the notion, Dwork's notion of rigidity, that everything is extended to whatever, unit ball, right, over compactification of closure, algebraic closure, right? And then presumably you can rediscover what Pasha discussed today. Presumably it is what they are doing with Sasha Varchenko, is with Andrei Smirnov, right? Pedically, it is pretty much, your answer is pretty much.
No, we are working actually, we are working over complex numbers.
It's pretty much the same, right? Trigonometric, why not? You will get trigonometric.
No, the main problem is, so we have, for example, quantum Knizhnik-Zamolodchikov equation, and it involves R matrices. And in some cases, these are matrices, so their matrices depend on the parameter polynomially. And in some simple cases, it is linear, but in general, for a general Lie algebra, they are not going to be linear. So we have to kind of get around that difficulty.
Yeah, but as far as I understand, Vanya maybe refers to this motivic story, something which
Work, actually, really, p-adic, motivic, you're absolutely right? And presumably, if you do it systematically, eventually you will get a story over in characteristic P, but maybe not the other way around. Of course, you will get.
Actually, you're correct. So there is another approach to this whole business, which is developed by Sasha Varchenko and Vadik Vologodsky. They are developing it, and which doesn't use this linearity. And it is they cannot handle yet all the examples that we can handle in our paper, but they have the big advantage that they don't have to use this linearity. And what they do is they use basically Hodge theory in characteristic P, and they show that p-curvature is going to localize on critical points of the master function, basically. And so this approach potentially can work in the Q-deformed case. And in the cases when it is known that difference equations are motivic, which means they have integral representation of solutions, which is true for a lot of examples.
Okay, so more questions? Well, if there are no questions, so Pash, thank you very much for very entertaining
Thank you for
interactive
Thank you.
talk.
Yeah, great
Yeah,
great event. Thank you.
Thank you.
Okay, thanks.
And this is it for today.